Associate Director at the Institute. Welcome to the boot camp for the program Satisfiability, Theory, Practice and Beyond. It's one of two programs that we're running this semester. The other is Theoretical Foundations of Computer Systems. And together they're involving around 120 long-term participants at the Institute. For those of you that weren't here for last week's boot camp, the boot camp's intended to get all of the program participants on the same page. In terms of the range of technical themes in the program. Also has a significant archival value as a sort of snapshot of the state of the art of the field. The talks are archived on YouTube and on our website. Let me introduce Jessie Gill, our events coordinator, who's here. Yeah. Hey, Jessie. Jessie's been dealing with the schedule and logistics for the bootcamp here at the Simons Institute, so big thank you to Jessie, and a big thank you to the organisers of the bootcamp: Albert at Sirius, Sam Buss, Vijay Ganesh, Antonina Kolokolova, and Jacob Nordstrom for putting together the program for this week. So thanks very much for all of your efforts. So I'll hand over to Albert to say a few words about the bootcamp.
Thank you very much, Peter. So welcome everybody to the first day of the bootcamp workshop for the Satisfiability program. And as most of you know, the bootcamps are supposed to be full-day events that would happen in Berkeley itself and would run for the whole week. But of course, because of the pandemic, we cannot do it this way. So instead, what we are going to do is that we ask the speakers to prepare pre-recorded lectures that they have posted already on the website. And so there will be a pre-recorded component and a live component. And today we are going to start with the live component. So the idea would be that experts would be able to hear the talks today without any preparation, but those who really need a tutorial, then the pre-recorded component serves that purpose. Still, today it's still a tutorial style kind of talk. That's how it's expected to be. So I want to start by thanking all the speakers of the bootcamp for the huge amount of work that they have put into preparing pre-recorded talks. It's a lot of work. It's many hours of recording, and it's very good quality work. So thank you very much for your efforts. So today we'll start with the first. So there are 5 days of bootcamp, and 4 of them are going to be tutorials delivered by a single speaker. And on Friday, we're going to have what we call applications. So on Friday is going to be slightly different. We're going to have 2 speakers, and they're going to give 50-minute lectures. But on Monday, Tuesday, Wednesday, and Thursday, we have distinguished lecturers who are going to tell us about specific areas within satisfiability. And today we are going to start with Valentine Kabanets, who is going to tell us about complexity theory centered around SAT. So Valentine is a professor at the Algorithms and Complexity Theory Lab at the Simon Fraser University in Canada. And he's a well-known expert in complexity theory. He has done very amazing work. So let me tell you a little bit about his work. In 2001, he obtained his PhD from Steve Cook. And the thesis was titled Non-Uniformly Hard Boolean Functions and Uniform Complexity Classes. So the work in his thesis included pioneering work on the minimum circuit size problem, which is today a central theme in complexity theory for its relevance for things like magnification and other very important trends in complexity theory these days. But this was in his thesis, but also very early work of his, perhaps also in the thesis or at least around his early times. He did some work with Russell Impagliazzo and Avi Victorson, which included what is today called the easy witness lemma. And this is a very important theorem in complexity theory, which is also a central theme today in what is known as the meta algorithms approach to circuit lower bounds, where algorithms for satisfiability play a very important role. So Valentine did very pioneering work in these two areas, and it's really important work. And I'm very happy that Today he's going to tell us about complexity theory centered around SAT. So let's get ready to enjoy his live lecture. I think he calls it Dancing with SAT. So Valentine, over to you.
Thank you very much, Albert, for the nice introduction. I want this guy to give a talk that you talked about. So let's see if that works. So can you see my shared screen?
Perfectly well.
Excellent. So good morning, good Berkeley morning, everybody, whatever time zone you're in. So this is the live part of the SAT-centered complexity tutorial. And the unofficial title is Dancing Around SAT because basically that's what we're doing in complexity. We're trying to understand what SAT is, how easy, how hard it is, and its connections to pretty much every other corner of complexity theory. And we're just exploring, and we'll keep exploring probably for a long time. So SAT has lots of connections to many things, in particular to NP-completeness, of course. That's the main thing that SAT is known for, but also polynomial time hierarchy, probabilistically checkable proofs, interactive proofs, and so forth. And that's some of the things that I talked about in the pre-recorded part of the tutorial, which has some background information. Today's tutorial will not be really building on top of this pre-recorded stuff from earlier. So for people who haven't watched it, it's fine. It will be fine. You'll be okay. And I'll talk about some other things that I left for the live part of the tutorial. Complexity of SAT, like exponential time complexity hypothesis and related stuff, and some connections to surrogate lower bounds. And we'll see if I have any time left to talk about something else. So talking about SAT, let's remember what we're talking about. 3SAT is the famous problem. Given 3CNF like this one here, is it satisfiable or not? And later on, we'll talk about KSAT. So this is just the formula where each clause is of size k or at most k, and usually we think of k as a constant. We know from Cook-Levin's theorem from 50 years ago that this problem 3SAT is very difficult. It captures the complexity of a whole bunch of problems in a class NP. It's one of the NP-complete problems. So we know for sure that if you can solve free satisfiability in polynomial time, then you've done great work. You solved pretty much every problem in NP in polynomial, not pretty much, but every problem in NP is solved in polynomial time as well. Well, there are still papers being written about SAT being in polynomial time. We far from getting there or even believing that this is actually possible. And it's still $1 million question to figure out the exact complexity of 3 satisfiability. So there are options of how complex this problem can be. So here's a graph of possibilities. So on the left side, you have polynomial time complexity for KSAT, and here will be usual measure of complexity. It will be the number of variables in a given formula. So we want to solve n-variate KSAT problems in time polynomial in n or some other non-trivial function in n. So polynomial in n, polynomial time is probably out of the question. So this is like the most optimistic scenario. But there are other possibilities. Even if p is different from np, it could be that SAT can be solved, say, in quasi-polynomial time, like n to the power polylog n. That would be quite good. If that's not true, we can move on and say, okay, how about sub-exponential time, like 2 to the n to the epsilon for every epsilon? Not as good as quasi-polynomial, but still quite non-trivial. We're not there anywhere near. So how about slightly better than exponential, like 2 to the little of n to the epsilon n for any epsilon? we're still not there. And what we do know for old versions of SAT is how to solve it in brute force, which of course take time to the n times some polynomial factor by trying all possible assignments to formulas. And so we can do here, and we don't believe polynomial time. And, you know, it seems like at the moment we're working somewhere around this regime of complexity of SAT. And rather than assuming that SAT is not in polynomial time, it may be worthwhile to consider a hypothesis that SAT requires exponential time, like to the omega n, and see what happens. Maybe we can disprove it, maybe we can have some other connections. So it's a fact, or it's a theorem, proved by many people from different directions, and I hope to talk about it a bit later today. What we know about algorithms for K-SAT? Well, basically, we know something non-trivial. We know that K-SAT can be solved in a randomized time, which is exponential, but exponential not just in n, but exponential in n times some quantity like 1 minus 1 over k. If you think of k as a constant, then 1 minus 1 over k is a constant less than 1. So this gives you time better than 2 to the n, okay, with a multiplicative constant in the exponent there. And different directions, different algorithmic approaches, starting from late 80s and happening until now and still happening, achieve pretty much the same bound. This constant here, which I denote as 1, is actually some constant c. Depending on the algorithm, it may be different c, but I'm going to ignore that for now, just a constant. And I'll hope to give you one such algorithm a bit later. But the point is that we don't have very fast algorithm for K-SAT, so let's formulate this hypothesis saying that, you cannot solve K-satisfiability in sub-exponential time. And that's exactly what Russell Impagliazzo and Mohan Paturi said in around 1999. And they formulated this so-called exponential time hypothesis, which said what I said. Free satisfiability cannot be solved in time 2 to the little o of n and some polynomial factor. And it's a hypothesis because, as Russell likes to say, the hypothesis rather the conjecture, meaning that whichever way you answer would be very interesting. Okay, so if it's true, if exponential time hypothesis is true, this is the left branch of the answer, then we know that P is different from NP and much more. We have much stronger bound than just SAT is difficult for polynomial time. And if the hypothesis is false, that's fantastic. You have some very non-trivial algorithm for solving K-SAT. And such an algorithm must have come with some interesting techniques, some structural properties about SAT that may be pushed even further and get even better algorithms. And not only do we have an algorithm for K-SAT, non-trivial algorithm for K-SAT, but also for other problems. And I will talk about this connection to other problems later on. We'll talk about so-called Sparsification Lemma. But first, let's think about this excuse me, sequence of problems like 3-SAT, 4-SAT, 5-SAT, and so forth. It seems like as k increases, your problem K-SAT should get harder, intuitively speaking. Is it getting strictly harder as k grows? We cannot answer unconditionally, but assuming that SAT cannot be done in sub-exponential time, the answer is indeed yes. As k grows, K-SAT gets harder and harder, strictly harder and harder. And that's one of the results proved by Mohan and Russell in the same paper where they talked about exponential time hypothesis. So it seems like K-SAT getting harder and harder, and as k gets bigger, the running time that you need for solving K-SAT approaches more and more closely the trivial brute force runtime of 2 to the n. Is it really true? It seems so. Okay, so let's formulate that as another hypothesis. Why not? We cannot solve SAT for large k significantly better than 2 to the n. So let's call it strong exponential time hypothesis. Again, introduced by Russell and Mohan with his student Calabro in around 2009. And it says that no matter how small epsilon you choose trying to get to the time to the n times 1 minus epsilon, for whatever small epsilon you choose, there will be a large enough constant k such that k sat cannot be solved in this running time to the 1 minus epsilon times n. Okay, so even getting close enough to the n, but be below to the n is very difficult, and some large k sat for large k will show you that that's not possible. So that's the strong exponential time hypothesis. And again, it's a hypothesis, so there are interesting implications each way. So if the hypothesis is false, then you have, of course, somewhat non-trivial algorithm for k-sat and other problems. Let me focus more on the direction if the hypothesis is true. So if it's true, then you're basically saying that the brute force lower bound, the brute force algorithm for SAT, which takes time to the n, is basically optimal. You cannot improve upon that. So brute force is optimal and not only for k-sat, for which the hypothesis is formulated, but it was noted and proved by many people that other NP-complete problems have the same behavior. Brute force algorithms for those is optimal. So you cannot improve upon the trivial to the n time for those problems where it's non-trivial time. And there's this whole area of research dedicated to studying the exact exponential time complexity of such NP-complete or NP-hard problems called exact exponential time algorithms. They use strong exponential time hypothesis to argue the optimality for many of their exact exponential time algorithms. But it's not only true for exponential time algorithms. Actually, this hypothesis, strong ETH, is so strong that it can be kind of translated down to the level of polynomial time, and you can prove some highly non-trivial results about the optimality of even polynomial time algorithms. And for example, you can show things like, assuming strong ETH, your basic algorithm scores algorithm for edit distance, which takes quadratic time, is actually optimal. And this area of complexity theory also has a name. It's called fine-grained complexity theory, pioneered by Virginia Vasilevska-Williams and Ryan Williams, and lots of other people have contributed in this active area of research currently. And there are some amazing results saying that these algorithms, like quadratic time algorithms, for example, that people have discovered for a long time now, and we're working very hard to try to improve, actually cannot be significantly improved unless you also violate the strong ETH. So unless you get a better algorithm for satisfiability. So working on edit distance is the same as working on satisfiability. You can't get away from satisfiability. You have to keep dancing around that. But you tell me, we don't know any such good k-sat algorithm that to talk about even time like 2 to the n better than 2 to the n. So what we do know, what I mentioned to you, and what I will hoping to show you later today, is that all known k-sat algorithms take time to the power n times 1 minus 1 over k, or 1 minus ck for some constant c. And we don't have anything better, even though we try different ways. Can we solve k-sat, an actual question, can we solve k-sat in better time than this? So can we improve this bound 1 minus 1 over k to something which mentions maybe some small growing function of k, like log k over k or log star k over k, anything non-trivial growing, super constant growing function? We don't know how to do it. Okay, so why not formulate that as another exponential time hypothesis? And that's what Ryan Williams did, actually giving a talk at Simons that was dedicated to fine-grained complexity and exact algorithms, exponential time algorithms, a few years back, he termed this super strong ETH, super strong exponential time hypothesis, which basically says that you cannot beat to the n times 1 minus 1 over k runtime for k-sat. Okay, this is like getting very fine-grained and very crazy, saying like, whatever we know for k-sat right now is the best. And I think it's like the purpose of this statement is more to encourage people to work harder and try to get a better algorithm for k-sat and even for unique k-sat. So a couple of years ago, Ryan with student Vyas proved that this super strong ETH is false for the case of random k-sat. So the classical algorithm due to Paturi, Pudlak, and Zain, PPZ algorithm actually works quite well on random k-sat formulas sampled near the threshold of satisfiability and achieves time to the power n 1 minus log k over k. So you can get log k over k savings for random case. For general case, we don't know how to get any better saving than what constant over k gives us. But another interesting observation, non-trivial result in Ryan's and Vyas's paper is that if you want to understand the complexity of k-sat algorithms without loss of generality, you can focus on the case of unique k-sat. And this is the case of k-sat where you're given a formula, KCNF, and you promised that the formula is either unsatisfiable or it's satisfied by exactly one truth assignment. So it has a unique satisfying assignment. And the case of unique k-sat is actually a very interesting special case that people like to consider. And it's often the first test case for analyzing proposed k-sat algorithms. It's usually easier to analyze the performance of a given k-sat algorithm for the case of unique k-sat. And as far as the super strong ETH is concerned, to break that, it's enough to improve a unique k-sat algorithm beyond what we currently know. So if you get a better than to the power n times 1 minus 1 over k algorithm for unique k-sat, then you're done for general k-sat as well. So there's a very nice sub-exponential time reduction in that paper. And we can actually probably start a new page of like complexity zoo for exponential time hypothesis because there are more. There was another so-called non-deterministic strong ETH that was proposed by Russell, Mohan, and a few of their students in 2016. Non-deterministic strong ETH. I'm not going to talk about that now. What I want to talk about is a very important tool, which is heavily used in many of these results around ETH and strong ETH, called Sparsification Lemma. And this is a result from the paper by Ipaglazzo, Paturi, and Zain around 1998. And that's what I would like to talk about next. Of course, if there are any questions at any point in time, please ask, chat them. And I'm monitoring the chat feeds on chat and the question and answers. So please don't be shy if there's anything that I need to specify more precisely. So roughly speaking, the Sparsification Lemma says that the hardest k-sat instances are those which have linear number of clauses. Okay, so you're given a KCNF, as usual, it's n variables, and we'll use m to denote the number of clauses in the KCNF. And a priori, if you have a KCNF, then the number of clauses can be as big as n to the k. So you can have polynomially many clauses in general. But it turns out that the linear case where the number of clauses is just some constant times n is the hardest one with respect to sub-exponential time algorithms like to the little of n time algorithms. So Vijay is asking about the number of variables, number of clauses. Yeah, so I'm addressing this question right now, talking about Sparsification Lemma. So yeah, many of these results, and I'll hope to show you an application of Sparsification Lemma, allows you to prove that exponential time hypothesis rules out fast algorithms, not just for KSAT, which hypothesis is formulated for, but also for some other problems that you get by reductions. But reductions have to be very special. And yes, preserving, keeping the number of clauses linear, the number of variables is crucial. You shall see, hopefully, in a moment, an application of this. So Specification Lemma basically says that you might as well focus, develop your best algorithms for KSAT for the case of linear number of clauses and number of variables, constant ratio between clauses and variables. As a corollary, you get the following result, which ties in nicely with what Vijay was asking me, I think. So fix any constant k bigger than or equal to 3. Why at least 3? Because 3 sat is NP-complete, and anything bigger than 3 is NP-complete. Then you have the following implication. If you can solve KSAT in sub-exponential time, where the input parameter is thought of as the sum of the number of variables and the number of clauses. So if you have an algorithm which runs in time to the little o of the number of clauses plus the number of variables, then you also get a KSAT algorithm with running time to the little o of n, where n is just the number of variables. So if somehow magically, mysteriously, you manage to get a fast algorithm which takes advantage of the number of clauses and runs in time to the little o of m, then you can always unwind this magic and make an algorithm for KSAT that will run in time to the little o of n for the number of variables n. And to the little o of n is really what we want to get, because to the n we can always get. To the little o of n is going to be very surprising, and this reduction kind of closes this strange possibilities that you can have an algorithm that runs in too little of number of clauses, but maybe no algorithm that runs in too little of number of variables. That would be very strange. And Sparsification Lemma says, no, that's not going to happen. We can always do this reduction. So assuming this reduction here, here's what you do to prove that some other problems in NP-complete problems are also exponentially hard. Here's an application. There's a classical NP-completeness reduction that you will probably see in any class on algorithms or complexity and teach to your students, saying that you can reduce 3 satisfiability to 3 coloring. 3 satisfiability, 3 coloring is a problem where you're given a graph and you want to know if it's possible to color the nodes of the graph using 3 colors, RGB, such that no edge gets the same color on its endpoints. Very famous, very well-known NP-complete problem. There's a standard classical reduction that takes CNF, 3 CNF, formula phi on n variables and m clauses, and in polynomial time reduces it to the graph G on vertices V and edges E, such that the number of vertices is going to be constant times the number of variables plus the number of clauses in an input 3 CNF. And the reduction satisfies the satisfiability preserving condition that says that phi is satisfiable if and only if the graph G constructed as a result of the reduction is 3 colorable. Okay, so why do we do these reductions? We want to say, well, if you can have a good algorithm for 3 colorability, if you have, say, polynomial time algorithm for 3 colorability, then you also get a polynomial time for 3 SAT. So that's what you get immediately from the NP-completeness reduction, classical reduction, like I described. But what if you only get slightly better than exponential time algorithm for 3 colorability? And in fact, you can get something non-trivial for 3 colorability better than to the n time, to the time n. So you can do to the power some small constant less than 1 times n. So you can beat to the n time for 3 colorability. How far can you push it down? Can you make an algorithm for 3 colorability that runs in time to the little o of the number of vertices in the graph? What would prevent you from doing so? Turns out exponential time hypothesis will prevent you from doing so. If you can get a running time for 3 colorability to the little of the number of vertices, then by this corollary I just described earlier, you get that 3 SAT is solved in time to the little of n as well. And that, of course, violates the exponential time hypothesis. So let's see why. It's very simple. suppose I start with algorithm for 3 colorability that runs in time too little of the number of nodes. Then, then by the classical reduction that I mentioned earlier, you get that 3sat is solvable in time to the little law of the number of vertices when you do the translation from 3sat to 3 colorability becomes n plus m. So little of the number of vertices becomes little of the n plus m. Okay, and then fortunately we have sparsification result, which says that, okay, if you have too little of n plus m algorithm, then you get too little of n algorithm as a result, and that violates exponential time hypothesis is done. So the conclusion is that under ETH, not only you cannot do 3sat in sub-exponential time, but you cannot do 3 colorability and quite a few other important NP-complete problems in better than exponential time. You cannot make them sub-exponential time complexity. Okay, so this is just one illustration for one problem, but it's a more general phenomenon that Russell and Mohan talked already in their original paper, and there was much more work done later afterwards. Okay, so how do you do this reduction from solving satisfiability for an arbitrary KCNF to just needing to solve k-satisfiability for KCNF with a linear number of clauses only? That's exactly what Sparsification Lemma tells you how to do. So let me formulate Sparsification Lemma. Fix any k, at least 3. Then basically for whatever epsilon you want, there will be some constant c such that you can constructively build from a given input KCNF phi on n variables with whatever number of clauses a list of KCNFs psi1 to psi t, where t is going to be sub-exponentially small, like 2 to the little of n to the epsilon n, such that your original CNF is satisfiable if and only if one of this psi1, psi2, psi t is satisfiable. Actually, it's even more than that. Your original CNF phi will be exactly equal, logically equivalent to the disjunction of this new KCNFs psi1 through psi t. So all the satisfying assignments are preserved. And to check satisfiability of phi, you're going to check satisfiability of each one of the psi i's, and each one of the psi i's will be a KCNF on linear number of clauses. Okay, so you take your formula, you sparsify it, but you cannot output just one. You have to output a whole bunch of formulas, sparse CNFs formulas, but fortunately not too many, only like to the epsilon n. And this is constructive in that there's an algorithm that I'm going to show you in a moment that will spit out this formula psi1 to psi t in time proportional to the number of such formulas, polynomial to the epsilon n. So this is the statement. Let me explain the algorithm. The algorithm is very simple. The analysis is not very complicated either, although I'm not going to do the analysis today, but I want to show you the algorithm. So let's call the algorithm Sparsify. It takes as input formula phi and outputs a list of sub-exponentially many sparse KCNFs. So input is a KCNF phi on n variables, and we think of clauses given as a list of clauses like so. And the first thing you do, and you'll do it also recursively, is you'll use this clause subsumption rule, which says that if you have two clauses, but one of them is contained entirely in the other one, then you might as well drop the longer one and keep the short one clause only. In this case, in this example, you have clause not x3 or x5, and then you have clause not x3 or x5 or x7. This one is bigger, so we can subsume it away and remove this clause. And so we have fewer clauses. And now we think of our clauses as sets, and we can draw them like sets of literals like this. And then, so the first step of the algorithm is do clause subsumption, eliminate unnecessary clauses to simplify the formula. And the second one is find a sunflower, go pick flowers. So what is a sunflower in this case? You'll try to collect together a large constant number of clauses of the same size so that they all have a shared part. So they all have some common part, which is called the heart of the sunflower. So it's an intersection of all the clauses, hopefully non-empty. And you want to make it as big as possible. And the rest, each clause without the heart, is called a petal. Okay. And so you want to find a sunflower, which means you want to have a large number of clauses, C1 through C lambda, such that they have a large intersection. And there are many of them. Okay. So I'm not specifying the details of the algorithm, but basically the algorithm focuses on the case of even if your formula has clauses of different sizes, you only look at formulas at clauses of the same size when you're looking for a sunflower like this. And you also favor short clauses. So you try to form a sunflower from the short clauses first, like clauses of size 2, for example. And also when you have larger clauses that you try to build a sunflower from, you favor large hearts. So you want to find the largest possible intersection first with enough clauses. And if you cannot do that, then you lower your expectations and you try to find a sunflower with smaller heart, smaller center, and you try to do that until you verify that until you find a sunflower, or you verify that there is none. And if there is none, if no sunflower can be found, then you say, I'm done, output phi and halt. And this case is not hard to see why you stop. If you stop in this way, then you know that your formula is already sparse. And this is a very simple application of the pigeonhole principle. Okay, so if there's some variable which appears in a large constant number of clauses, then this variable, or this literal rather, will be a heart, non-trivial heart of a large sunflower. Okay, so the only way for you to stop this algorithm is that each literal appears in constant number of clauses only, in small constant number of clauses only. And that means that the number of clauses itself is also only linear in the number of variables. Okay, so when you stop, you get a sparse formula. That's easy to see. The petals shouldn't be disjoint, yes. So this is it's a weak sunflower rather than a strong sunflower. I didn't want to make this distinction in the description of the algorithm. So usually in combinatorics, people define a sunflower that pairwise intersections are the same for different sets, for different pairs of sets. Here, you can have a clause, like in my picture, C1 and C2, they also share a variable x1, which doesn't make it into the heart. But yeah, petals are not disjoint, even outside the heart. Don't have to be. Yeah, we're not using, in the analysis here, we're not using anything super complicated about like sunflowers that mathematicians study. It's much simpler argument, like pigeonhole principle based, basically. So what happens if you did find a sunflower? Then you do the split and recurse. So you take your formula phi, and you form two subformulas, phi1 and phi2, by plucking your sunflower and putting the heart on the one side and putting the petals on the other side. Okay, and of course, by subsumption rule, the heart will kick out all the clauses that contributed to the heart in the next recursive iteration, and the petals will kick out all the clauses that they came from. So in the first case, you make definite progress because you kicked out a whole bunch of clauses and replaced them with a single heart clause. So that's obvious progress. In the second case, you have not reduced the number of clauses per se because petals are still there, but each petal is now shorter than it was before. So than the clause it was before. So you're making progress by reducing the size of the clause, even though you don't make the number of clauses smaller necessarily. And once you build these two formulas, you recurse and you sparsify phi1, output the list that you get this way, and then sparsify phi2, output the list you get there, put these two lists together, and you'll get your final list of sparse formulas as a result. Okay, so that's the algorithm. Hopefully the algorithm is clear. The analysis of the algorithm, as I mentioned, is not very complicated, but somewhat technical. So you need to analyze this backtracking procedure and keep track of the progress you make. And there's a bit of complication because the progress in the pedal case is not obvious, but it's possible to analyze this case and say that if you think about your algorithm as kind of backtracking procedure and you have different branches, then the total size of this binary tree will be at most 2 to the epsilon n if you pick your constants right. So basically, you cannot add too many clauses to your formula on any single branch, and that shows you that the size of the branching, the size of this tree will be better than trivial 2 to the n size, but rather 2 to the epsilon n size. Okay, so there's a bit of savings that you can do by carefully choosing your parameters, like this constant lambda that I mentioned here. Actually, it's not a single constant lambda, but it also depends on the size of clause that you're considering now. So you have a whole sequence of constants lambda sub I, depending on the size of the clause C. If it's clauses of width 3, then you have one constant. Clauses of width 4, you have a different constant appropriately defined as a sequence. And yeah, it's a careful balancing act to analyze this algorithm, which I'm not going to do now. Okay. Any questions so far? Okay, great. So I'm actually, well, somebody has a question that they don't understand enough. It's just a statement. So, sorry, can you be specific? Can you ask a specific question? What is not clear? I'm actually going much faster than I thought I would, so it's good that people stop me and ask questions. Okay. Good. So that was Sparsification Lemma and exponential time hypothesis related stuff. And the next thing I'm going to do is to talk about this non-trivial K-SAT algorithms. And maybe I'll introduce this thing now, and then we'll take a short break because it's like a separate part of my talk. It would be nice to have a separation between the two. But what we're going to do after the break, assuming that the chair, Albert, agrees with taking a break.
Of course, yes, perfectly.
Thank you. What we're going to do after the break is talk about this algorithm for K-SAT. And let me just tell you this story now. So I mentioned that we have a non-trivial running time algorithm for K-SAT, where it runs in time exponential in 2 to the n to the power 1 minus 1 over k, where k is the width of the clauses. And interestingly, there are different ways you can try to get an algorithm for K-SAT. And even though they kind of look different, they all converge on the same runtime at the end. So I'm just mentioning a few of those threads. Backtracking thread, which are famous algorithms PPZ that I mentioned earlier, Paturi-Pudlak-Zane, and then there's a beefed up version of that, Paturi-Pudlak-Sachs-Zane algorithm, PPSZ. The constant over k here gets better, but it's still some constant, and the running time is what is shown. Then there's a wonderful algorithm using some kind of randomized local search due to Uwe Schoening from around 1999. Very different idea from, or supposedly different idea from this backtracking algorithms of PPZ and PPSZ, still the same runtime, roughly, again, constants change. And then you're using some circuit complexity ideas. Chen and Williams in 2016 used the polynomial method, which is a circuit lower bound technique that we love and use in proving lower bounds for constant depth circuits in complexity theory. So you can turn this around and use the circuit lower bound proof techniques to get algorithms, and you also get the same runtime. So like, no matter what you do, what we know, and try different things that we know about KSAT, you end up in the same place, which leads some people to suspect maybe that's the right place, or at least, as in the case of super strong ETH, it leads people to say, okay, let's formulate this as a challenge, as a question, as a hypothesis, and try to work even harder to disprove that. So what I'm going to do after the break is show you another algorithm for KSAT, which won't only be an algorithm for checking satisfiability of a given KCNF, but will do more for the same price. It will count the number of satisfying assignments in the same runtime that I mentioned, to the power n times 1 minus 1 over k. Okay, and we'll use so-called switching lemma. That will be the main tool that I want to talk about. Which is a tool kind of similar to the polynomial method that people love and use to prove surrogate lower bounds for constant depth circuits, known as AC0 circuits. And this tool this is basically an algorithmic tool, can also be turned around and used to prove, to analyze the algorithms, to analyze KSAT algorithms. And that's the algorithm from the switching lemma for sharp KSAT is from the paper by Impagazzo, Matthews, and Paturia from around 2012. And so I'm going to tell you all about it, or a lot about it, after the break.
Okay, so we're taking the break now?
Yeah.
All right, so let's then resume at 1860. Sorry. So for me, it's
Berkeley time.
So let's resume in 5 minutes. Let's say that.
5 minutes. Okay. Great. Thank you.
So one thing I wanted to say is I'm not seeing all the questions for some reason. Do I have all the rights to see? Because
so the only questions I see were the ones in the chat. That was the only channel that was posting something. On the question and answer channel, I don't see anything.
You mentioned the question by VJ, and I don't see that.
Yeah, that was on the chat. That was on the Zoom chat.
Maybe it was directly to Valentine or something.
Oh, maybe it was. Yeah, it was directly to me. Yeah, that's right. Yes.
Okay.
From Vijay, it was directly to me, direct message. Okay, yeah. And also from Pavel, also direct to me. Yeah, so that's why you didn't see those questions.
Okay,
they were direct questions to me.
Yes, I don't try to spam everybody with questions.
No, but don't be shy, because others may also want to ask the same question, but are very shy. So lead the way, Pavel, please.
I just want to ask one thing. So you have this 1 minus 1 over k in the exponent, but these algorithms differ in that in the numerator it's not 1, but it's some constant.
That's right. That's right. Yes, it will be some constant.
Exactly the same in instance. But
So,
you are going to talk about it probably.
Yeah, I'm going to talk about a particular constant that we'll get from the switching lemma, and will not be as good as the constant you get like in PPSZ, for example.
But as you presented it, you said that it's always 1 over k, which is...
No, I did mention, I tried to mention, I thought I did mention that it's going to be always some constant c over k, and this constant c will change depending on the algorithmic approach. Yeah, for different algorithms, it will be slightly different constant, but it's always going to be some constant over k.
Okay.
Yeah, and sometimes it's bigger than 1, sometimes it's less than 1. But asymptotically, it's like 1 over k. So I don't want to clutter. Maybe I'm confusing people this way, but yeah. Thank you, Pavel. Yes, that's a good point. And of course, people do care about this constant and try to improve it for special cases and still write papers of getting better and better analysis of various algorithms. Yes.
Okay, so according to my watch, it's been 5 minutes. Is it correct?
All right. The chair has spoken.
let me just say one thing. There's going to be a gather.town meeting for all of us at the end of your lecture. So I will post the link. Everybody's invited to come in, and some of us will be there. I believe Valentine might also be there, maybe. Will you come to gather.town?
Yes, yes.
Perfect. So, okay, so I'll post the link at the end of your lecture. So please go ahead.
Yes, yeah, I'll try to answer to Massimo's question, but Ryan beat me to it. Yeah, it's a deterministic algorithm, the Sparsification algorithm. It's completely deterministic. You just look for the sunflower, find the best one if it exists, and then you deterministically split and then keep going. Yeah, so there's no randomness needed. Good. Okay, back to the KSAT algorithm. So as I mentioned, this theme of satisfiability is pervasive through complexity theory, and the SAT is the gift that keeps on giving, and we're still studying it. And even when we think we do something else, like proving circuit lower bounds, we're still working on SAT algorithms, it turns out. So let me explain to you how that happens. So to talk about the switching lemma, I need to explain to you a simpler model than KCNF model, the model of decision trees. Okay, so I'll draw a picture for you. So decision tree is binary tree. So let's say you have want to compute a function, some function f in 5 variables, x1 through x5. You can do it in this model where in the node you query a variable, and depending on its value, whether it's 0 or 1, you keep going on the left branch or on the right branch of the tree. And so you keep querying variables, labeling the nodes of the branch, and based on the value of the variable in your input, you keep walking until you reach a leaf, and the leaf is maybe labeled by 1, in which case you output yes or accept or 1, or the leaf may be labeled by 0, in which case you output 0 or reject. And the natural parameter of this decision tree is the depth, which is the length of the longest branch in the tree. Okay, so it's a very nice, very simple model. It's much simpler than KCNFs or KDNFs because it's very easy to show that if I have a depth D decision tree, then I can convert it into DCNF or DDNF, whichever I like. Okay, so basic idea is that I just gonna encode each of the branches by conjunction of literals. So for example, here, this branch that goes to 1 will be encoded by saying not x1 and not x2. That's what will take me to this particular leaf. And then I'll do the same thing for other branches that take me to decision 1. And this will give me disjunction of conjunction of literals. And this will be my DNF in this case. And if I want to do a CNF, then I'll just take the decision tree for the negation of my function f by simply swapping zeros and ones and do the DNF for that, and then do negation again, and negation of DNF becomes a CNF for my original function. Okay, so both DCNF and DDNF are very easy to do. Okay, hopefully this is clear. Why do we like decision trees? Well, they're so simple that satisfiability is very easy to answer if you give any decision tree. Well, you just look at the decision tree and see if you have any leaf labeled by 1. If so, then you have satisfiability. Answered yes, right? There's a way to get to the 1 by following some branch, so that will give you a satisfying assignment. Well, it will give you not just a satisfying assignment, but you can also count how many satisfying assignments there are. And the reason for that is that different branches of the decision tree focus on completely disjoint subsets of assignments that take you to those leaves. So the assignments which take me on the leftmost branch are those which have x1 set to 0 and x2 set to 0. And the other three variables, x3, x4, x5, don't matter. So no matter what they are, and there are 2 to the 3, 8 assignments possible, all of those possibilities will be satisfying assignments. So this branch here is responsible for 3 to the 3 satisfying assignments. And the second branch, this one here, is responsible for assignments which start with 0, 1, and then have 0 for variable x4. But the other 2 variables are completely unrestricted. And so you can get another 2 to the 2 satisfying assignments for the second branch. And note that those 2 branches talk about completely disjoint sets of assignments. The reason is, like, if you take a particular assignment, there will be unique path in the decision tree you have to make. So it's not possible that the same assignment will take you to different leaves. You have a unique branch that this assignment will follow, and that's the region that this assignment will go. Okay, so all the regions are disjoint, and moreover, you know the size of each region of assignments that take you there by looking at the length of the path that took you to that particular leaf. So length of the branch gives you enough information to count all possible satisfying assignments. And so that leads you to this following simple fact, that sharp-SAT for depth D decision trees can be solved in time proportional to the size of the decision tree, which of course is at most 2 to the power the depth of the decision tree. Okay, and formula that I mentioned before. Sharp-SAT you can count by looking at branches labeled by 1 and doing this calculation exponential in n minus the length of the branch. Okay, so small depth decision trees are fantastic because not only can you answer SAT, but you can also do count SAT efficiently, sharp-SAT efficiently. How are we going to be using this? Intuitively, well, given an arbitrary KCNF, it's probably not going to have a small depth decision tree to begin with, but we're going to try to help it, encourage it to become a small decision tree by setting some variables to some constants, and we'll do it randomly using the notion of a random restriction. And the switching lemma that we're going to be using is the fact that says that if you take an arbitrary KCNF and apply a random restriction, meaning that you set some variables to constants with some parameters of the distribution, then with very high probability, your KCNF will become a small depth decision tree. And then once it's simplified like this, it's very easy to do like satisfiability or even count satisfiability problems for your restricted CNF. Of course, you need to worry about different restrictions. So you'll see that you'll basically try all possible restrictions. And since with high probability, they will make the formula simple, most of those restrictions will make the formula simple decision tree. And that's, you can answer the sharp-SAT question there very easily. And for some rare occasional cases where your restriction does not make the formula simple, you have to work hard, but that doesn't happen very often. So all in all, you'll save over the brute force to the n runtime this way. I'll give you more details now, so it's just trying to give you a preview of what's coming. So let me explain what the random restrictions are. So you have this 2 parameters, n for the number of variables in your CNF, and L is for the number of variables that will be left alone, that will be left unassigned constants. So they will stay, they will survive, they will live. You pick a random subset of the variables, so subset S of indices between 1 and n, of size exactly L. And for each index I outside of S, you'll pick a random bit, B sub I, and then your restriction of the variables x1 through xn will be defined as follows. For each variable I, rho of that variable is going to be the same, xi, if the variable was left to live. It's in the set capital S, and there will be like L such variables. Or if the variable is outside, it will be replaced by constant, randomly chosen 0, 1 with probability 50-50. Okay, so after this random restriction, exactly L variables will live, and the rest will be replaced by randomly chosen constants 0 and 1. And the switching lemma says that if I start with a KCNF, and I pick a random restriction R with appropriately chosen parameter L, then with high probability, when I look at the restriction on my formula phi under this raw, and I build a decision tree from it, which can be done in a straightforward way, in a naive way. You can always try to build decision tree from your CNF by looking at each clauses in turn and building decision tree from each one and putting them underneath each other. So it's notion of a canonical decision tree that you can do constructively. Then this decision tree will have small depth with very high probability over the choice of a random restriction raw. Okay, so that's the statement. Informally, here's a more formal statement known as Hostas switching lemma from around 1987. It says that for any parameter p between 0 and 1, if I start with a KCNF phi, and for any parameter s, which will be the parameter on the depth, the probability over the random restriction R raw that has parameter L, the number of variables that will live, set to be exactly p times n. Okay, so p fractional, excuse me. So exactly p fractional variables will be surviving. So with probability all but 7pk to the power s, the resulting CNF phi, when I apply the restriction, will become a small depth decision tree. The probability that the decision tree will have depth bigger than s decays exponentially fast with s. Okay, so that's the important thing to remember here. Bigger than depth s happens with probability exponentially small in s. Why exponentially small in s? Because we can always choose the parameter p any way we like, and we'll choose it to be something like 1 over 15k, so that 7pk becomes smaller than 1/2. And so this is exponential decay in the depth s. Okay, so the point is that very likely your decision tree will be small depth. So how are we going to use that? So here's a sharp k-SAT algorithm. Given as input KCNF formula phi, it will be a randomized algorithm, but it will be a zero error algorithm, meaning that it will never make a mistake, but sometimes will not give an answer. Actually, what we're going to show is that this algorithm is going to be run in expected small time. So it will not make a mistake, but sometimes may be slow. But with high probability, it will be relatively fast. It will have time that I mentioned, to the power n times 1 minus 1 over 15k. So what's the algorithm going to do? It will pick a random set S of size Pn, not a coincidence here. I mean, Pn is exactly what the switching lemma was telling us about. So you pick a set of the right size, and you pick P to be sufficiently small, like 1 over 15k. Again, not a coincidence, because that's what the switching lemma parameters want us to do if you want to have exponential decay of having large depth when the formula is hit with a random restriction. And then we do the following computation, exponential time computation. So we have the set S of live variables, and then we try all possible settings bits B. There are n minus Pn variables that will be fixed in all possible ways. Okay, so for all possible way of fixing the remaining n minus Pn variables, you look at the restricted formula phi, where those variables outside of set S are fixed, and the variables in set S remain free. And then you take your formula phi after this restriction, build a decision tree from it in the canonical way. And once you have a decision tree, you solve sharp SAT in the way that I described earlier. You look at the branches, see how long the branch is, and this will give you the count for each of the regions corresponding to the leaves of the decision tree. Okay, so that's the algorithm. Okay. So algorithm clear? So obviously the algorithm never makes a mistake because it does the exact computation. Okay, so it splits the assignments into regions, disjoint regions. It doesn't overcount because all the regions are disjoint, and it doesn't miss anything because it tries all possibilities for this bits B. Okay, so this is an exact algorithm. We just need to analyze the runtime of this algorithm. So the correctness is obvious. What about the runtime? Okay, and I can analyze the runtime exactly. So I'll give you the complete proof. I'll give you the complete analysis here. It's only a few lines, so that's why I can do it. So let's analyze the expected runtime. So it's going to be a random variable of the random choices made by the algorithm. The only random choice is the choice of the set S at the very beginning of the algorithm of this size, p times n. And giving this random choice, the runtime will basically be proportional to how many possible assignments you need to make to the remaining variables outside of S. And you see it's basically going to be some exponential in n minus pn. And we want to keep it this way. And we want this to be our final time. So everything else must go away somehow. So you do the summation over all possible to the n minus pn assignments. And for each one, you'll do the sharp SAT computation for the restricted CNF formula phi, where the restriction comes as the set S of the variables that stay alive and the bits B of that you fix the remaining variables outside of S to. Okay. So let's try to analyze how much this time is going to cost us. But we're going to make some tricks. So instead of thinking of this sum as the sum, we'll try to convert it into the expectation. How we can do that? Well, we're just going to multiply and divide by 2 to the n minus pn. Okay. And then we'll take this part outside here. And the other part, 1 over 2 to the n minus pn, is like the probability under the uniform distribution of picking this one particular b. So the summation after the proper multiplication with the proper 1 over 2 to the n minus pn thing becomes an expectation over all possible b's. And now we can merge the first expectation with the second expectation and just write it as a single expectation where you pick a random set S and then you pick a random assignment B to the variables outside of S. But what does that remind you of? This is exactly the random restriction raw, the way I defined it earlier. You pick a random set and then you randomly assign variables outside of S. So let's call it what it is, a random restriction raw that comes from the distribution script R with the parameter Pn. Okay, so with a simple trick, we converted our expected runtime to a much nicer expression, which has this huge bound in the front. And the rest is just some expectation, which talks about the restricted CNF phi under a random restriction raw coming from the distribution about which we know something. We know something from Hostas switching lemma. Okay, there's one more simplification I did going from the top line to the second line. Remember what the time of sharp SAT for the decision tree is. So if you're given a decision tree of certain depth, then to solve sharp SAT, you just need to go through all the branches of the tree. So the time it takes you to solve sharp SAT for decision tree is the size of the decision tree, which can be upper bounded by the 2 to the power the depth of the decision tree. Okay, so this time of sharp SAT of decision tree is upper bounded by 2 to the power depth of the decision tree that you get from phi under the restriction raw. That make sense? Okay, so with simple observations, we made our life so much easier now. All we need to do is to talk about this expectation of random restrictions of this exponential quantity to the depth of the decision tree phi that you obtain from phi when you hit it with the random restriction raw. Okay, so we'll leave the left multiplication term as is, and the expectation of a non-negative integer variable can be written as the sum over all t's of the probabilities that this variable is bigger than or equal to t. Okay, that's another simple observation, that you can write expectations of integer valued variables as the sum of the probabilities, or the probabilities are of the event that the variable exceeds some integer threshold t, and you range from t from 1 to infinity. Okay, good. So making progress. Now, this quantity here, I want to talk, instead of talking about to the depth bigger than t, I want to talk about depth bigger than t, or depth bigger than s, actually, because remember what Hostas switching lemma told us. They gave us it gave us a nice bound on what probability is there that the decision tree has depth bigger than s. And what I have now is something like to the depth of the decision tree. Okay, so I want to convert to just the depth of the decision tree. So I need to take like logs on the both sides of this expression here, or put differently, I want to change my summation from integers t to powers of 2. So I want to go, instead of bigger than or equal to t, I want to go bigger than to the power s, and I want to try all possible s from like 0 to infinity. Okay, so I want to change from all integers to just powers of 2 integers. Of course, when I do so, I miss out certain integers that were there, but no longer there, because I only focus on the powers of 2. So I need to take that into account. And how many integers do I miss when I go from 2 to the power s to 2 to the power s plus 1? I miss exactly in the middle, I miss exactly 2 to the s integers. Okay, so those which I don't count anymore, so I need to multiply by this quantity explicitly, and then look at this same probability as before. And this way I can go from my summation over all integers t to summations over all powers of 2 with an extra multiplicative factor inside. Okay. But that multiplicative factor, even though it's huge, to the power s, is not going to bother us, because Hostas switching lemma has very strong exponential decay. And we choose p appropriately so that we overwhelm this exponential to the s in the probability that after the restriction, the depth of our decision tree for the CNF phi becomes bigger than s. What is going to be? Hostas tells us it will be 7pk to the power s. We chose p with foresight, so that this quantity will be 7/15 to the power s. Okay, so we plug in 7/15 in here, and we get 2 to the s times 7/15 to the s. It's only 14 over 15 to the s, strictly less than 1, magic. And then the summation of this geometric series just converges to some constant being 15 in this case. So this whole expression becomes constant 15 times to the n to the power n times 1 minus 1 over 15k, as promised. Okay, so that's the whole proof. And the constant you get here is not as good as you get in some other algorithms, but this is a counting algorithm as opposed to just satisfiability algorithm that you get from other approaches. And if you ignore the constant, which of course people care about and try to analyze the algorithms very precisely to figure out what the constant is in front of the 1 over k. But if you ignore that, then asymptotically it has the same runtime as all these other k-sat algorithms, but it gives you more information about k-sat formulas by allowing it to count in addition. Any questions? Is that clear? Okay, so I'm basically getting towards the end of my talk. Okay, so Paul is asking a question. I guess, is it easy to say what the best constant C is known, such as the saving CK in the exponent? Yeah, no, it's not easy for me, at least, to say what the best constant C is. I think, yeah, thank you, Navid. It's pi square over 6, I guess, for general K. There were some improvements for maybe unique K-sat, some improvements to PPSZ that were published recently. I'm not sure what the exact constant they get there. They get some improvement. Yeah, from that paper of stock 19, they get some improvements over the original PPSZ, but I wouldn't be able to tell you exactly what the improvement is. I know that for like case of 3-sat, if you write your your expression in the exponent, the base to the power n, and the base is some constant less than 2, then the improvement over PPSZ for the case of unique 3-sat is like in the third digit after the dot, decimal dot, like 1 point, blah, 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 something, 1 less than the previous one. But yeah, it's very difficult for me to say what would be the exponent C. Pi squared over 6 is bigger than 1. I think that's pretty clear. So PPSZ and other related algorithms can get savings C over K, where C is bigger than 1. What I've shown you just now, C over K is for C equal to 1 over 15, which is less than 1. Okay, great. So what we've seen is that circuit lower bound techniques, this polynomial method I mentioned earlier that Chen and Williams used to prove, to construct a SAT algorithm. I think they also get sharp SAT algorithm in their paper. It seems like the circuit lower bound techniques are a bit more powerful and allow you to do the counting, not just satisfiability. And so you get SAT algorithms, not just for, excuse me, you get SAT algorithms not just for the case of KCNFs, but, and this was an important line of research, you also get circuit SAT algorithms for various classes of circuits for which we can prove circuit lower bounds. So this result that I just told you about, switching lemma based algorithm for counting satisfying assignments for KCNFs has actually been used in that paper of Impaglazzo, Matthews, and Paturi to get count-SAT algorithms for AC0 satisfiability, where AC0 satisfiability is like an extension of CNF satisfiability, where instead of a simple formula which has ends of ORs, you have more complicated formulas which have ends of ORs of ends of ORs, some constant depth. And those are more complicated than just KCNFs. You cannot get a good algorithm for those things if you try to reduce them by applying something like Cook-Levins reduction from circuits to KCNF formulas. You have a significant blow up as you do so, and then your savings for KCNF will be irrelevant. So you need to tackle directly the question of satisfiability for those more complicated models of computation like circuits. And it turns out that for those weak models of circuits for which we can prove lower bounds, which means that we kind of understand those models of circuits well enough to reason about them, we also usually can extract SAT algorithms for those circuit satisfiability questions as well. And so this example of switching lemma is used to get AC0 constant depth circuit lower bounds, and then you can do similar things with other weak models of constant depth circuits, which we can prove lower bounds for. So once you have circuit lower bounds for a circuit class, you get a SAT algorithm for this class, usually. But also the other way is also true. If I have a non-trivial SAT algorithm for some circuit class C, and non-trivial needs to be specified, and basically it means that you better than brute force, so you better than time to the n. But then there's a question of like how much better, and also for which size of the circuits. So you always fix the input size to be n, but then the circuit size may vary. It can be just polynomial in n, it can be weakly sub-exponential in n, like 2 to the n to the epsilon, for example. So it depends on what kind of exact circuit SAT question you're talking about. And non-trivial can be you do better than 2 to the n by polynomial factor at the bottom, 2 to the n over poly n, or you do better by sub-exponential factor, like 2 to the n divided by 2 to the n to the epsilon. So all of those things can be called non-trivial savings for circuit SAT algorithms. And for the right choice of non-trivial, you get this connection due to Ryan Williams that says that if I have a non-trivial SAT algorithm for a circuit class C, then I also get lower bounds for that circuit class C. Okay, so it's kind of going in the opposite direction. Before we said from circuit lower bounds you get SAT algorithms. Now we're saying from SAT algorithms we get circuit lower bounds as well. Okay, so SAT algorithms keeps giving and is connected to circuit lower bounds in both directions. And actually, depending on the non-trivial, like the lower bounds you get can be made for a function which lives in a class almost NP. It's non-deterministic quasi-polynomial time. So it's like non-deterministic time n to the polylog n. Okay, so this is the complexity class non-deterministic quasi-polynomial time. Of course, NP would be fantastic, but even quasi-polynomial time functions in quasi-polynomial time, proof circuit lower bounds for those is great. Yes, Vijay is again asking me a question directly. Yeah, when I talk about circuit lower bounds, I do refer to super polynomial lower bounds in general. Of course, exponential lower bounds would be better, and sometimes we can get exponential lower bounds. And again, exponential, you can have different notions of exponential. As in runtime of SAT algorithms, you can talk about strongly exponential or sub-exponential or weakly exponential. But basically, like circuit lower bounds we have, for example, for constant depth circuits, have the form 2 to the n to the epsilon, and that's the best we know for constant depth circuits. We don't have 2 to the n lower bounds even for constant depth circuits, so that would be the dream. And for the results I mentioned here, the lower bounds you get as a conclusion from the SAT algorithm, usually also of this kind, because they cannot really outperform the lower bounds that we have for those circuit classes. And in the techniques we have don't seem to give us super strong exponential lower bounds. But yeah, that's a very interesting question. Yeah, the point is that like we have different approaches to proving circuit lower bounds. The traditional classical approach, like Hostas switching lemma, that I mentioned earlier, is more like combinatorial in nature. You stare down at your model of computation and you try to understand its properties. In switching lemma's cases, the properties of KCNFs. And okay, what property KCNFs have under random restrictions? They simplify nicely. Okay, fantastic. This is the property we're going to use to show that something like parity, which cannot be simplified no matter how hard you hit it with the random restriction, it remains parity when you fix some variables to constants. This parity cannot be computed by constant depth circuits. So this kind of very combinatorial approach, which gives you circuit lower bounds for functions which are very simple function, like parity, for example, functions in polynomial time even. In contrast, this SAT algorithm-based approach to lower bounds can only handle functions pretty high up there in space, like in non-deterministic quasi-polynomial time, or even non-deterministic exponential time, or even higher, depending on the quality of SAT algorithms we're talking about. But they have a different approach. They really exploit this algorithmic connection. The better SAT algorithm you have, the more powerful SAT algorithm you have, the stronger lower bounds you get. And the lower bounds use SAT algorithms in a very indirect way that I don't have time to go into. But basically, it combines this combinatorial approaches, sometimes by saying that we understand the circuit class well enough to explain it in terms of this combinatorial property, and then you use the standard complexity theory machinery for uniform Turing computation using so-called diagonalization arguments, old results that come from Cantor and from Turing that you can diagonalize against small time and bigger time. So combining those combinatorics and uniform complexity results, you get this circuit lower bounds from SAT algorithms. And it's a very interesting direction. And surprisingly fruitful because even for a special case of circuits, we can show an application of this approach to say that non-restricted quasi-polynomial time does not have polynomial size constant depth circuits where the constant depth circuits allow to ask mod 6, for example, questions. So you allow mod 6 gates in addition to your standard AND, OR, and NOT gates. And proving a lower bound for this case of constant depth circuits with composite modular gates was a big open question for many years. The combinatorial approaches seem to be stuck. The SAT approach worked out fantastically well. And it based on the combinatorial characterization of ACC0 that we knew about and with some other clever ideas to push this whole argument through. Okay. So that's pretty much all I had to say for today's tutorial. There's a lot of things to talk about. And when I was preparing this these tutorials, I had some grandiose plans in mind, like how many things I'll be able to cover and talk about, because SAT is connected to so many different things. And there are so many interesting stories out there that you can talk and talk and talk. So I had really to be very conservative and like cut myself in terms of how much I can cover. But SAT will continue to be the fundamental problem in complexity theory. And we're going to be stuck dancing around SAT until maybe one day we'll understand the complexity of SAT well, whenever that day comes. And until then, we're still going to be exploring and covering the properties of SAT, connections to other things, and SAT will become the central sun-like problem for complexity for many years to come. I have another question from Vijay.
Before you take the question, let me just thank you very much for this very beautiful talk.
Thank you very much.
So I think we started already with the discussion. So let's continue a little bit. People, please ask on the chat or unmute yourself, and you can also ask.
Yeah, so Vijay is asking for SAT algorithm for circuit class, what do I mean? Does the algorithm directly deal with the circuit representation, or is it converted into a CNF first? No, it's not converted anywhere. It's direct circuit. So you give me an actual circuit, describe the actual circuit with all the connections, with all the gates and all that, and I will answer the circuit SAT directly. If I try to convert it anywhere, then I have to introduce new variables, and that will blow up the input size. And then even if I have relatively good CNF SAT algorithm, the savings I'll get there will be blown away by the increase in the input size, the instance size that I'll do during the reduction. So that's what I mentioned, that you cannot really deal with everything by converting it to KSAT, because the quality of KSAT algorithms known today is just not enough to overcome that blow up in the instance size. So you need to work directly with instances as they're given. So circuit SAT is for circuits.
So I have a question myself, that connecting the two parts, the first two parts of your talk today.
Mm-hmm.
So when you told us about the sparsification, well, the main result there is that the number of clauses is not relevant for getting these sub-exponential algorithms.
Right.
And then in the second part, you gave a an algorithm with this running time where you were using the switching lemma, which intriguingly doesn't use the number of clauses. So the switching lemma is independent of the number of clauses. So the question is this a coincidence, or is there a way to get, for example, sparsification from the switching lemma? Could they be connected in some way?
Yeah. So actually I'm not sure. So people have tried to get sparsification for more general model like constant depth circuits, and I think it's not possible, if I remember right. But in terms of like the number of clauses, so for this AC0 satisfiability result of IMP, you actually generalize the switching lemma to something more, which takes into account not just a single CNF, but a whole bunch of CNFs. And that's kind of like the sparsification thing, in the sense that the number of CNFs will influence the overall efficiency of your algorithm. And so the classical result is talking about a single case CNF, but when you have a AC0 circuit, then you can imagine that you have this constant depth construction, and at the bottom two levels, you have the CNFs hanging off, and you have a whole bunch of them. And you want to analyze the effect of the random restriction, not just with respect to a single CNF, but like the whole collection of the CNFs together. And you want to argue that like a random restriction will simultaneously simplify all of them. And for that, you need a generalized version of the switching lemma that was proved in the paper by Palazzo, Matthews, and Paturi. And around the same time, using the original proof techniques of Hostas, Johann Hostas also proved a version of that switching lemma. So we also have like a complexity zoo, little complexity zoo of switching lemmas now. We have the original switching lemma, then we have this generalized switching lemma, which is called multi-switching lemma, which is a bit difficult to state, so I'm not going to state it now. And then, of course, we have switching lemmas in proof complexity that I used to prove great new improved lower bounds for constant depth formulas. So sparsification versus switching lemma, I'm not sure if there's any connection. I wonder if anybody, maybe somebody knows, like Russell, Ryan?
Well, in any case, the floor is open for more questions.
Yeah.
So can you hear me?
Yeah.
Yes.
Thanks again, Valentine, for a great talk. So quick question, what if, with regard to the sparsification lemma, imagine if you knew more about the structure of a class of instances, would that enable you to somehow further strengthen this lemma, like, and in general, analysis of some of these sub-exponential algorithms, has that been explored? So for example, the only parameters you seem to consider are the width of the clauses, in addition to the size of the input as measured in terms of the number of variables. But what if I had other parameters? Typically when I think about instances obtained from real world applications, they tend to be highly structured, and they're not, they have no resemblance to the random classes of formulas or that you consider. By random, I mean uniformly generated at random.
Yeah, it's an excellent question. Like, can you have some natural restrictions on the class of formulas and say something non-trivial, maybe even more non-trivial than what Specification Lemma tells you? That's your question, right?
Yeah.
Yeah, I'm not aware of anything along those lines. Again, I think Russell is on the line somewhere. Maybe he knows. He's the Sparsification Lemma originator. That would be great. And I know it's connected to other things that people are, and part of this SAT special semester will be about, of trying to understand what makes SAT algorithms that we have today work well, what kind of properties of instances they exploit. And yeah, I think that ties into that theme of what kind of properties of sophisticated general classes of formulas there are that will lead, and we can explain the success of SAT algorithms, or maybe like structural properties of those formulas that can be exploited by backtracking style algorithms. Yeah, so yeah, Sparsification Lemma, as you see, is a very natural kind of backtracking algorithm analyzed. So it's
Russell has a note.
Russell
Sparsification
says,
is worst case. So.
Yeah, so sparsification is a very general statement. So it says something for the worst case. So linear density is the hardest case for the not just for average case, but for worst case. So it's a more general statement. Yeah, but I guess the question was like, can you make a less general statement which will take advantage of some structural properties of your formulas, rather than saying that it's anything, clause, the number of clauses can be anything, the structure can be anything. You can always do the DPLL style algorithm and reduce it to sparse case in sub-exponential time, but can you do better if you know more? Yeah, I think.
So it looks like some people want to ask questions orally, but we should grant them access. I don't know how to do it. Maybe Jesse, are you there? So I think one has to give a panelist, how do you say, permission or whatever it's called. And I don't know how to do it. So there are some more questions on the chat or
the comments. I see some comments from Russell in the chat.
So Mohan wants to ask, for example, but I don't know how to give him.
Mohan, can you unmute?
Oh, okay.
Are you able to unmute?
No, apparently not.
Ooh.
He's not a panelist. Someone needs to promote him to panelist.
Yeah.
That's the word. Yeah. I don't know. I mean, I don't have permissions to promote people to panelists.
Jesse, can you do that?
Yes, Albert, I think you do have permissions.
How do I do it?
You go to the attendees list, and what's the name?
What is the question?
So you go to the attendees list, and you click more, and then under that it says promote panelists.
Okay, so let me see. Attendees here. Here, more, promote to panelist. Okay, so now it's done. So Mohan should be able to speak now.
Excellent.
Yeah, this is wonderful, and I could speak now, and the Zoom closed and opened again so that I can speak. Mine is only a small comment to Vijay's question. Structure may or may not help. For example, if you take the parity problem, block parity, that already has, that cannot be specified further, and it's a highly structured formula. And maybe there are other ways by which we can exploit structure to improve the circuit. Not sure that unspecified will do that.
Were you able to hear the question, Valentine?
Not really. I think, yeah, it was difficult here. I think he was talking about some sparsification.
No, I heard the comment by Mohan. I think Mohan was saying that it was in response to my question, which was about structure, and the answer was that structure may or may not help. It depends on the setting. I think that's how I understood Mohan's comment.
Right. You can't hear me, Valentine?
Yeah.
Parity is block parity is an example.
Block
parity. And it cannot be specified.
Cannot be specified, yeah. Right. Yeah. Yeah, parity is a very hard function for CNFs. So if you have some kind of block parity function, then you won't be able to specify it a lot, because parity cannot be written down as a small CNF, a K CNF, for that matter. I guess that's the point. Yeah.
Okay, any other questions? Naveed has a question. Graph theoretic structures can be used. Formulas of a small tree width can be solved more easily.
Yeah, of course. But does it?
A comment rather than a question.
It's a comment. It's not a question. Yeah. Yeah.
Okay, so let me post on the chat the link for gather.town, and we could move there and continue our conversations, maybe with the speaker or maybe between us. So let me post it here, if I manage. Or maybe Antonina, can you put it, because I'm not able to do it, if Antonina is around. So let me conclude this session today by thanking again Valentine for this beautiful talk, and also by announcing or encouraging you to look at the videos if you haven't done it yet, especially Valentine also, because he covered many classical topics of complexity theory, including proximate counting. I mean, he was talking about the Valley and Vasirani reduction to unique set, which appeared today during the talk. But also this technique of hashing is also quite relevant, because on Friday we're going to hear a talk on approximate counting in a practical setting using set solvers, and the methods for that Kuldep will be telling us about are using these methods of approximate counting that were developed in a theoretical framework first with hashing, and then they become into a practical technology. So it's really worth looking at these videos that Valentine did, and I encourage you to do it. So thank you very much, everybody.
Thank you very much, Albert.
And I think now gather.town is already in chat. Yeah. Bye-bye.